Hello everyone and welcome to Euclid Book 1 Proposition 4. So this one is a little bit different. This is our first proof proposition, so we're really making an argument instead of constructing a figure, and the goal, as you'll see here, is to prove that this triangle is equal in every way to this triangle here. Usually when you're doing the proof propositions, your drawing does not need to be as precise, since it's really the logical reasoning that matters, not the picture, but having a good picture is helpful, and in fact I have drawn these two triangles so they are in fact the same. And then, as you'll see here, in modern geometry textbooks, this would be called a side angle side proof. So if you see side angle side in another book, or SAS, this is the side angle side proof for Euclid. Comes very early. Basically, we're going to prove that this side equals this side, or assume it. Rather, we're going to assume if this side equals this side, this angle equals this angle, and this side equals this side, then as you can see in the order, side angle side equals side angle side. And then the whole point of this proof is to show that if side angle side equals side angle side, then the two triangles are equal in every way. Well, the other thing I'd say is the way this proof proceeds is it's sort of a proof by coincidence, meaning you sort of just imagine sitting one triangle on top of the other. And it's fine. It's a valid proof. It works fine. But I will say proofs like this I feel like make mathematicians a little bit queasy. We worry a bit that maybe we're fooling ourselves possibly with this kind of proof, but this is the way this proof proceeds anyway. So Euclid 1 Proposition 4 reads, if two triangles have the two sides equal to two sides respectively, and have the angles contained by the equal straight lines equal, in other words, the angle between them, they will also have the base equal to the base, the triangle will be equal to the triangle, and the remaining angles will be equal to the remaining angles respectively, namely those which the equal sides subtend. So he's just saying that if these two sides are equal and the angle between them is equal, then the base also equals the base, and the two angles here subtending those two sides, or here and here subtending these two sides, will also be the same. So let ABC and DEF, right here, be two triangles having the two sides AB, AC equal to the two sides DE, DF respectively, namely, and then I'll go ahead and write the proof out as we go here, namely, AB is equal to DE, so this side equals this side, and AC is equal to DF. So this side is equal to this side here. And the angle BAC equal to the angle EDF. So there we go. Boop, boop. So and the angle BAC equal to the angle EDF. In other words, the angles at the top. Then Euclid proceeds. I say that the base BC is also equal to the base EF. The triangle ABC will be equal to the triangle DEF. He's thinking the area is there. So the area of triangle ABC will be equal to the area of triangle DEF. And the remaining angles will be equal to the remaining angles respectively, namely those which the equal sides subtend. That is, the angle ABC to the angle DEF, in other words, this angle will equal this angle, and the angle ACB to the angle DFE, in other words, this angle will equal this angle. Okay, and then he proceeds with the proof. 4. If the triangle ABC be applied to the triangle DEF, so I'll proceed here. Whoop, yeah, I was right. This was a little persnickety. There we go. So the claim is that the triangles are equal, and we're going to do that by, the proof will be, there we go, apply triangle ABC to triangle EDF. In other words, imagine the two triangles sitting on one another. And then Euclid says, and if the point A be placed on the point D, and the straight line AB on DE, then the point B will also coincide with E, because AB is equal to DE. So in other words, I proceed here, you want to imagine putting point A on top of point D and sort of lining up line AB with line DE, okay? But we already said that line AB is equal in length to DE. So if A is sitting on top of D and this line is sitting on top of this line and these two lines have the same length, then it must be the case that point B is also sitting on top of point E. Okay, so we've sort of developed now the left side of the triangle. Then Euclid continues, again, AB coinciding with DE, the straight line AC will also coincide with DF because the angle BAC is equal to the angle EDF. Hence, the point C will also coincide with the point F because AC is equal again to DF. So in other words, if I click here again, but then the argument is that AC must coincide with DF. Since these angles are the same, okay, and this line is sitting on top of this line, then it must be the case also that this line is sitting on top of this line. Okay, we got that. But we already said that this line is the same length as this line. So if they're sitting on top of each other because the angles at the top are the same, then it must also be the case that C will coincide with F. Okay? And so now we've proven that the 3 points coincide with the 3 points, which indeed is going to mean that the triangles are the same. But just to continue with Euclid here, Euclid says, but B also coincided with E. We already said that. Hence, the base BC will coincide with the base EF. So just to write that out here. We already said that B coincided with E. So it must be the case that BC is equal to EF. Okay, since they're just traveling between the same 2 points. So the 2 triangles are equal in every way. So we're basically done. To finish what Euclid says here, thus the whole triangle ABC will coincide with the whole triangle DEF and will be equal to it. And the remaining angles will also coincide with the remaining angles and be equal to them. The angle ABC to the angle DEF, and the angle ACB to the angle DFE. Therefore, etc., being what it was required to prove.